Hi guys, I think most of you should, not most of you, I think all of you should have already finished your prelim, and I think some of you probably are already getting back your results, and I'm hoping that you are happy enough with your results. And today we are going to be continuing with our live stream doing paper 2. I'm trying to get hold of hello I'm trying to get hold of the 2020 prelim paper, so maybe in the next few weeks, if I'm able to get hold of them, we can do some some 2020 papers together. But for now, I'm going to continue with 2019 papers, and this Eunoia 2019 paper 2 seems to be a pretty good paper for us to try. I have not done section A, but I think the statistics portion is going to give us a good experience, because some of the questions are actually a little bit more difficult. And I just want to remind you guys again, that when you are doing a paper 2, and now that most of you have had already finished your prelim, when you are doing paper 2, as much as possible, you should try to start with statistics first. Where I was just talking to one of my students, and he was telling me that it was such a good strategy, to do a paper 2 by starting off with statistics. Timing wise, getting yourself motivated and warm up wise, it is just going to be a better experience during the exam. So when he was talking to his classmates, he was telling me that he was a bit surprised, and I was also a little bit surprised that there are still some people starting with the pure math portion of paper 2 first, which may or may not be a good idea, but it is a risk that I think we do not need to take, especially when it comes to our final exam. So yeah, we're doing stats first. I totally agree with you. Okay, hello, because I think doing stats first is definitely going to be something that will help you to do better in general for your paper 2. So I encourage you guys, okay, if you have not tried this yet, please do consider starting off with your statistics first, especially now that you guys are going to be having some time trial here and there. Your school will probably be organizing these time trials for you. You can try, what if you were to start with statistics first? Most likely you will score higher just because you plan this ahead. Okay, anyway, let's take a look at this Eunoia JC paper together. We are going to start with question number 6. Okay, let's take a look at question number 6. So for question number 6, it is a discrete random variable question. We are looking specifically at a bias die with 4 faces. The numbers are 1, 2, 3, and 4. The probability distribution table is given to us as this. And the question didn't really define, but we are trying to look at the number on the face of the dice. So I think I'm going to do a definition. Let me try to define. I'm going to let x be the number shown on the face of a randomly chosen die. So a randomly chosen die. And since now that you guys have already finished your prelim, you will probably, I think you probably have gotten back your paper 2, right? So you should see how marks are going to be allocated, or marks to be deducted if you didn't define your discrete random variable or define any random variable that you have used. So I'm defining x as the number that is shown on the dice, which means that in part 1, in order for us to find an expression of d in terms of c, I'm going to make use of the fact that for a probability distribution table that is given to us, if I were to sum up all the probabilities, it is the probability when it is trying to sum up the probability when x is equal to x. When I sum up all the probabilities, it should be equal to 1. So the probabilities will be 0.3 plus C plus D plus 0.2. This is equal to 1. It is a very easy 1 mark to get. We are supposed to express D in terms of C. So D here is going to be equal to 0.5 minus C. Let me record it down here. So we have found that D is equal to 0.5 minus C. And part 2, we are supposed to write down the variance, and it is going to be in terms of this. So we can see that most likely variance is going to be expressed in terms of C, and it is going to be a quadratic equation in terms, a quadratic expression in terms of C. And in order for us to get an expression that is like this, it is most likely, we most likely would have to be applying the completing square to the quadratic expression that we are expecting. So to find the variance, let us try to first find the expectation of x. So the expectation of x is going to be sum of all the x multiplied by the corresponding probabilities. So this is going to be 1 multiplied by 0.3, then plus 2 multiplied by C, plus 3 multiplied by D, then 4 multiplied by 0.2. Like what we were saying, because of the way the question asks us to answer, we know that we are supposed to write variance in terms of C. So for the expectation, I'm going to try to express it in terms of C. So what I will be getting now is going to be a 0.3 plus 0.8. That gives me a 1.1 plus 2C plus 3D. And D is 0.5 minus C. So if I were to simplify this, the expectation is going to be equal to 2.6 minus C. We will find the expectation of x squared with the aim that I'm going to make use of this and this to find the variance of x, which we can subsequently re-express into a form that is like this. So to find the expectation, we will sum all the x squared multiplied by the corresponding probability of x is equal to x. So it's going to be 1 square multiplied by 0.3 plus 2 square multiplied by C square and 3 square multiplied by D square. So actually not C square, it's multiplied by C. Then 3 square multiplied by D, and then 4 square multiplied by 0.2. X multiplied by the corresponding probabilities. And this is going to be equal to 3.5. Then plus 4C plus 9 times of D, which we can rewrite this as D is 0.5 minus C. So expectation of x squared will be 8 minus 5C. And now we can find the variance of x. And the variance of x will be the expectation of x squared minus away the expectation of x, the whole thing squared. So expectation of x squared, that will be 8 minus 5C, then minus away expectation of x, which is this 2.6 minus C squared. So we have 8 minus 5C minus away 2.6 minus C square. 2.6 square, this is equal to 6.79. Then minus away 2 times this times C, this is going to be equal to 5.2C, then plus C square. And the variance of x, we will be getting a quadratic expression in terms of C. That will be minus C squared plus 0.2C plus 1.24. We will complete the square for this, because like what the question requires us to do, we are supposed to rewrite it into this form, which is the completed square form of a quadratic expression in terms of C, and then listing down alpha, h, and k. So let's try to complete the square for this. Maybe I'm going to factorize out this negative from the C square. So it will be this minus 0.2C minus away 1.24. Completing square, I will make sure that the coefficient of C square is always positive before I complete the square So we have this minus 0.1 square minus 0.1 square minus 1.24. And finally, expanding this, I'm going to be getting a negative c minus 0.1 square plus 1.25. And now we can compare it to this and we can realize that alpha is going to be equal to 1 and h is going to be equal to 0.1 and k is equal to 1.25. And now with the completed square form, we should be able to quote the value of c that cause variance to be the maximum. For the variance to be maximum, when it is in the form of this, we know that this, with respect to variance, let's say variance is the y-axis. So let me just try to do a rough sketch of what that is happening here. So if let's say variance is going to be on the y-axis and c is going to be on the x-axis, so we have this. Okay, maybe let me just call this the c-axis since we are writing everything in terms of c. So looking at this, we know it is going to be a parabola, which is going to be a set face. And from the completed square form, we know the maximum possible point here is when c is equal to 0.1 and the variance is going to y is going to be equal to 1.25. This is going to give us the maximum possible variance of x. Therefore, we can say that variance of x is maximized when c is equal to 0.1. This will be for part 2 of the question. And I think it is still pretty okay. It is quite a good warm-up. And that is this is exactly why I think we should all start with statistics first. Okay, because it gives us the quickest way to get marks and it also get us more warm-up to our H2 math. So let me erase this. Let's take a look at the last part. So for the last part here, we are looking at c to be equal to 0.2. And we want to find the probability that in 10 throws of the die, at least 7 throws land on an even number. For even number, we should be getting the number that is on the die as either 2 or 4. So the probability of getting an even number will be c plus 0.2. And the question tells us that c is equal to 0.2, which means that the probability of throwing a dice and getting an even number will be 0.2 plus 0.2. So we are talking about a probability of 0.4 to be getting an even number when we throw this die. And looking at the scenario here, this is going to be done 10 times. And for each throw, we are looking at whether it is an even number or an odd number. So what we are looking at here now follows, it fits the condition that we can then assume that this is following a binomial distribution. So let me define a random variable for this binomial distribution. I'm going to call it, let's say, y. And I'm going to let y be the number of even number. Out of the 10 throws. And like what we were saying, y here will follow a binomial distribution. Out of 10 throws, the probability for one throw to be getting an even number will be c plus 0.2, and that will be 0.4. And we are supposed to find the probability that there are at least 7 throws that will land on an even number. So it is when y is bigger or equal to 7. And to calculate this using our graphing calculator, it is going to be 1 minus probability that y is less than or equal to 6, since we want 7, 8, 9, 10. So we will minus away less than or equal to 6 so that we can press into our calculator binomial CDF. This is going to give us a probability of 0.0548. Question number 6. Let's move on. Let's take a look at question number 7. Oh, this is a very, very interesting question. Where I do find that this is a very interesting question because this question actually gives us a same yet different perspective of standardization for normal distribution. Okay. I see I see someone is trying to you gather more people to get the 5th November 5th November workshop that we have organized. This 5th November workshop is currently having an early bird promotion, so it will end tomorrow. So I'm really hoping that MC, you will be able to find 1 or 2 more people, because if you have 4 people and you sign at the same time, it's just $25. I mean, even after that, it is not going to be that cheap, but I mean, since there's an early bird discount, why not? Oh, you're in NS? Okay. Okay, I hope you'll be able to get some some more people to, you know, to to join with you to get the 5th of November workshop. On during the workshop, you know, we will definitely try to discuss all the statistics topics again. I believe it is going to be a good time, you know, that we can really sit down and reconsolidate all the ideas one more time just before you sit for your statistics. Most likely the things that, and I'm hoping, okay, that the things that I'll be discussing on that day are a good recap to you. Recap as in, like, you already know them, you know, but what we want to do is to try to rehearse them one more time, and I'm going to try to go a little bit deeper so that hopefully, you know, we can discover some areas of our statistics that maybe we are still a little bit unsure of, and the worst was we didn't even know that we are not clear enough about them. So hopefully during that day I can find enough chances for me to talk about them, you know, then hopefully it is going to be also adding value to your revision the night that is before. Yep, sure, I'm going to see you, MC, on that day. For 2 people, I think it is $45, right? $45 per person. Yeah. So anyway, let's take a look at this question number 7. Okay, it is really a very, very interesting question. It's not difficult. It is just that because of the difference in the perspective for this normal distribution question, I think it adds a bit of I think it adds a little bit of unfamiliarity into how we usually do a normal distribution question, and it is very, very useful to be practicing questions that are like this. So I'm glad we chance upon one question that is like this. We have x1, x2, x3. They are independent normal distribution, and for each of the distributions, the mean is a constant mu, and the variance is the one that is changing from x1 to x2 to x3 according to the formula that is given. The formula is variance of xn is equal to 2n, which means that if I were to be looking at x2, okay, let's look at x2. That means for part 1, for x2, according to the question, this will follow a normal distribution. It will follow a normal distribution with a mean as mu, and the variance is going to be 2n. So x2, n is going to be equal to 2, which means that we are going to have a 2 times of 2. So x2 will follow a normal distribution with a mean of 2 and a variance of 4. And we are supposed to find this. We are supposed to calculate mu minus 1, where x2 is going to be between mu minus 1 and mu plus 1. Okay, x2 is between this and this. And basically we cannot find x2 to be between this and this. Okay, because we do not have mu, and we need to go through our calculator to calculate the normal distribution, correct? So in order for us to continue with this, we need to make use of the core concept of standardization. The idea of standardization, I'm going to leave it to you guys to go and take a look at what I have on the Achevas TV theory outline. You know, in there, there's a little bit of derivation of how the distribution of Z is going to be like. But Z is a linear combination of X, a general X, where X follows a normal distribution. So Z is going to be of a form X minus mu divided by sigma, and this will always follow a normal distribution of 0, 1. X minus mu divided by sigma. So as long as I can create a X minus its own mean, a random variable minus its own mean, divided by its own standard deviation, and if X follows a normal distribution, then it will the linear combination of it will also follow a normal distribution with a mean of 0 and a standard deviation or a variance of 1. So what I'm going to try to do is to create the same effect here. So I'm going to take this x2, I will minus mu throughout. Mu as in like its own mean, which means that I have mu minus 1 minus mu. The same here, we will have mu plus 1 minus mu. A little bit lacking in space. Let me shift this away a little bit. So, and I'm going to divide this throughout by its own standard deviation, which is 2. So I'll divide this by 2. I'll divide this by 2. The inequality sign remains the same. And now once I've done this, which has gone through this linear combination, will give us z. So we are talking about z to be between minus 1 over 2 and 1 over 2. And now we have a probability that we can calculate, because z as a standardized normal distribution will have a mean of 0 and a variance of 1. And now we can press this into our calculator. I'm going to get the probability of this to be equal to 0.383. Okay, this is for part 1. And we are going to try something that is similar for part 2 and 3, as long as we want to use our calculator to do the calculation, especially when we will never be able to find mu. Okay, so we are going to be always working with an unknown mu in this question number 7, and yet we are going to try to find a way so that we can do a calculation like what we have just done here. Okay, that is why I do find that this is a very interesting question, giving us a whole new perspective on standardization. So for part 2, for part 2, I know what we are going to be analyzing. We can't possibly be calculating probability of x3 to be bigger or equal to x4. So what we will be calculating will be probability that x3 minus x4, this is going to be bigger or equal to 0. Okay, so we'll be looking at x3 minus x4. That is why I'm going to write down first the distribution for x3. x3 will follow a normal distribution with the mean as mu. That is what the question says. And the variance will be 2 times of 3. So this tells me that x3 will follow a normal distribution with mu and 6. I'm going to do the same thing for x4. x4 will follow a normal distribution of mu and 2 times of 4. 2 times 4 is 8. Okay, let me just write it down here in case you missed what I've said. It is 2 times of 4 that gave me this 8. So I have x3, I have x4, and now we can try to find the expectation of x3 minus x4 because of this that we are expecting ourselves to be calculating. So this will be the expectation of x3 minus away the expectation of x4. And it happens to be mu minus away mu. And this gives us a 0. So although mu is unknown, at least the expectation of x3 minus x4 is known as 0. And we are going to try to find the variance of x3 minus x4, which is going to be the variance of x3 plus the variance of x4. So this is going to be equal to 6 plus 8. This is equal to 6 plus 8. Goodness, 6 plus 8. This is equal to 14. So this tells me that x3 minus x4, this will follow a normal distribution with a mean of 0 and a variance of 14. Okay, so we have this. So x3 minus x4, it is this, which means that now in order for us to do the calculation for the probability of x3 bigger or equal to x4, okay, this is going to be calculated as probability of x3 minus away x4. This is bigger or equal to 0. And since now we have x3 minus x4 that follows this normal distribution, we can then press into our calculator with the lower limit as 0, upper limit as E99. Mu is going to be equal to 0 and sigma is going to be square root of 14. If I were to press this into the calculator, I'm going to get 0.5000, which is actually 0.5. So it depends on you, right? If you can just visualize this, on a bell curve. If you have already done that, you know that for this bell curve, the center here is going to be equal to 0. So what we are trying to calculate is the probability that is on the right hand side of 0. So it is this region here, which is half of the area of the bell curve. That is why 0.5 you can either press into your calculator or just simply do the deduction based on the shape of the bell curve. Okay, this is part 2. And part 3 is also very interesting. Part 3, I feel that for question number 7, 1 and 3, they are the most interesting. Okay, because of the way that we can do the calculation without knowing mu. In fact, it was supposed to be so in part 2, but I think EJC's teachers have planned this so well so that mu is like, just cancelled. So I'm going to get a 0 here, and we do a deduction based on the shape. But let's see how we are going to make use of something that is similar to part 1 to do part 3. So I'm going to leave this normal distribution, this standardized idea here, so that we know that we are going to be doing this again way later. Minus mu divided by its own standard deviation. So we now have this, and in order for us to work on the probability where yn is between this and this, let's try to first find the expectation of yn and the variance of yn. And please take note that x1, x2, x3, they are normal distribution, which means that when I try to do a linear combination of x1, x2 all the way to xn divided by n, which is a linear combination, we will be getting yn as also a normal distribution. So let's try to find the expectation of yn. And the expectation of yn will be the expectation of x1 plus x2 plus x3 all the way until xn divided by n. 1 over n is just a constant. I'm going to sort of like take out this 1 over n. So we'll be having the expectation of x1 plus x2 plus x3 all the way until xn. This is going to be 1 over n, and expectation of x1, which is going to be mu, right? All the mean are going to be mu. Expectation of x2 will also be mu. Expectation of x3 will also be mu, all the way until the very last one, which is expectation of xn will also be mu. How many how many x's are there going to be here? From 1 all the way until n. So we know that there are going to be n numbers of mu. So what we have here is going to be equal to 1 over n multiplied by n mu, and this is going to be equal to mu. So the expectation of yn is going to be mu. We are going to try to find the variance also. For the variance of yn, this is going to be equal to the variance of x1 plus x2 plus all the way until xn divided by n. 1 over n, which is a constant, I'm going to rewrite it as 1 over n squared if I were to take it out from the variance notation. Then we will have a variance of x1 plus x2 all the way until xn. So it is going to be a 1 over n squared. Then we are looking at variance of x1. Variance of x1 is 2 times 1. So let me write it down here, 2 times 1. Then plus variance of x2. Variance of x2 is 2 times 2. So we have this. And then variance of x3, variance of x4, all the way until variance of xn, which is this. And can you see what we have here inside the bracket here? It is 2 plus 4 plus 6 plus 8 plus all the way until 2n. So what we are seeing here is an AP. An AP with the first term as 2, and the common difference is 2 plus 2 plus 2 plus 2. So this is going to be equal to 1 over n squared. Applying now the sum of AP formula, we have n number of terms, because x1 all the way until xn, there are n number of terms, so n over 2. The first term, which is 2, plus the last term, which is 2n. So the variance of yn and n can be cancelled. 2, 2, 2, all these can be cancelled. So we have a 1 plus n over n. This is the variance of yn, and then according to the question, let us try to write down the distribution of yn first. So yn will follow a normal distribution. Since it's a linear combination of normal distributions, it has a mean of mu and it has a variance of 1 plus n over n. And according to the question, we are looking at probability that yn is going to be between mu minus 1 and mu plus 1. And this probability is going to be bigger than 2 over 3. With this inequality, we are going to try to find the smallest integer value for n. The smallest integer value for n. We cannot really press this into the calculator again. So I'm going to once again make use of the idea of standardization, where we know that in order for us to get z, it is going to take it is going to be the random variable minus away its own mean divided by its own standard deviation. So that's what I'm going to do now. I'm going to take yn minus mu throughout. So we have mu minus 1 minus mu throughout. Yn, I'm going to minus mu, and then mu plus 1, I'm going to minus mu. And we are going to divide this by its standard deviation, which is going to be square root of 1 plus n over n. So we have this square root of 1 plus n over n. Same for this, square root of 1 plus n over n. So it is supposed to be between this, and this is supposed to be bigger than 2 over 3. So we are now looking at the probability where this is now going to be z, okay? Which means that we are switching the normal distribution that we are working on from this to now z, which follows a normal distribution of 0, 1. And this, we can rewrite it as minus square root of n over 1 plus n. And this is going to be square root of n over 1 plus n. This is supposed to be bigger than 2 over 3. And I think it is easier, I've been telling you guys before, that many times it is actually easier for us to work on the other side of the inequality to be equal to 0, because it is going to be easier for us to compare, which means that I'm going to try to press this entire expression here into the y1 of my calculator, and I'm going to try to generate a table to search for where y1 is going to be bigger than 0. So I'm going to press this into the calculator. I think I have some screenshots here. Yes, I have. So I'm going to press this into the calculator. We can putting this into y1. So my y1 will be this, then minus away 2 over 3. And I will generate a table. Okay, let me show you guys my table. So after I've generated it. So this is my table. Let me put it here. So I've generated this table, and if I were to scroll through the table, I'm looking actively for when this entire expression, including the minus 2 over 3, is going to be bigger than 0, and this is where it happened. I'm going to present what I have in my table into my solution also. So we are looking at n versus y1, where y1 represents probability that this n over 1 plus n z, then square root of n over 1 plus n minus 2 over 3. So y1 represents this, and when n is equal to 14, this is equal to negative 7 times 10 to the power of minus 4, a negative number. When it is 15, we have a 4.1 times 10 to the power of minus 4. When it is 16, when it's 16, this is equal to 0.0014. So this expression started to become positive when n is equal to 15, and then subsequently 16 and so on. Therefore, the smallest possible integer, the smallest integer value of n is going to be equal to 15. Well, I'm hoping that you guys have tried this question independently, before I even go through, then at least, right, you can feel why this question is potentially why this can be a very good question to be attempting before your A-level. Because I do believe that every year, A-level will attempt to find at least 1 or 2 parts of your H2 math, and they will try to discuss a little bit deeper into those 1 or 2 parts. So for example, if they decided that for this time round, they want to discuss a little bit more about normal distribution, us going through an experience that is like what this EJC paper gave us, I think it's going to add quite a fair bit of value to how you're going to be reacting to your statistics on the day itself. Really, Claire, this is insane. I thought this is a very cool question. And I think in order for you to do this, you just need to do a very simple thing, okay, which is to really understand how standardization work. Like for example here, let me see the time. Actually, we have some time. Let me show you, just in case, okay, that any one of you have not actually known how this standardization work. Why is it that when you do this minus mu divided by sigma, then suddenly you're going to get a normal distribution of 0, 1. Let me show you something that is actually very simple to do. You can immediately try this. You don't even need to try this. Just take a look at what I'm going to be doing now. It is going to make sense. That means, for example, right, in case some of you have never actually derived the idea of normal distribution before, let me show you something, okay? It's really very easy. For example, right, if you have x that follows a normal distribution with a mean of mu and a variance of sigma square, okay, which means that if you are planning to press this into the calculator, you need the value of mu, you need the value of sigma square, just like this yn. If you don't have the values, it is going to be hard for you to press anything into the calculator to find the probability, right? So somebody actually found out that if you were to do a linear combination of x, and specifically if you were to try to take x minus its own mean, this is a constant, you must understand, this is just a number. So if you take x minus its own mean and then you divide by its own standard deviation, maybe through trial and error, I'm not very sure, but if you were to do something that is like this, where mu and sigma, they are just constants, let's see what it is going to become, okay, which means that I'm going to try to see what this distribution is going to become. I know it is definitely going to become a normal distribution because we are doing a linear combination of a normal distribution. So what we need here is going to be the expectation. What is sigma? Sigma is a constant, so this is going to be 1 over sigma. Then after that, expectation of x minus mu, correct? So 1 over sigma is still going to be 1 over sigma. We have the expectation of x. What is the expectation of x? That is mu. Then minus away the expectation of a constant, and it will be that constant. So mu minus mu. Wait, remember, this was from the expectation of x. So this is going to be 0 all the time, regardless of the value of mu, as long as you go, regardless of the value of mu or sigma, as long as you do this linear combination, the expectation will always be 0. What if we were to try to find the variance of x minus mu divided by sigma? 1 over sigma is a constant, so it is going to be 1 over sigma square, and we will have a variance of x minus mu. So this is going to be 1 over sigma square, and we will have a variance of x. Mu is a constant, so variance of a constant is 0. 0 has no spread, it is just going to be a constant. So we are having a 1 over sigma square, and hey guys, what is the variance of x? Isn't that sigma square? So we will multiply this by sigma square, which gives me a 1. That is why here is 1 all the time, which means that for any normal distribution, as long as you let it go through this linear combination, you will just be getting one that is of 0, 1 all the time. And since we are doing this all the time, let us just rewrite this as z. And that is how you are using z to be solving for this, because you don't have mu, you don't really have this 1 plus n over n. So what if we were to try to take this minus away its own mean, and divide it by its own standard deviation. And this will automatically follow a normal distribution of 0, 1. And then I can just press it into the calculator, in order for me to get whatever value that I'm supposed to be getting. Better than me not knowing too many. I mean, me not having mu. Okay, then and with n as also an unknown, there will be no way for me to press it into the calculator, right? I mean, these are the few things that we will be discussing again, on the 5th of November, so that for certain aspects of statistics, if it is possible for us to understand a little bit better, if it is possible for us to just spend a little bit more time to have a better grasp of it the night that is before, let's try to go for it. It may not appear in our A-level on that day, but at least we know we are more secure, okay, because our ideas and our concept are better grounded. And this kind of concepts, right, are going to be very easy for you guys to pick up, even if you have never known them before, because most likely by the 5th of November, which is today is the 29th of September, so probably in a month's time, you're going to be leaving your H2 subjects and probably also your H1 subjects like every single day. So you're going to be like a sponge. If you were to see something that is like this, it'll be so easy for you to absorb them. Next, let's take a look at this question number 8. 8 is pretty simple until when you reach part 4. And part 4, although it is difficult, but we definitely need to know how to do part 4 because it has came up, something similar to this has been coming out in Cambridge exams, I think 2010, and subsequently another 2 more years. So it has come out for at least 3 times in the H2 math exams. So it is definitely important for us to at least catch the idea of how to do something that is like part 4, because the question can always vary. Anyway, let's take a look at what we have. I mean, the information that we have first. Probability of A is given to us as this. I guess this we can try to visualize it on a Venn diagram. So if I have A and B, I know this area here is going to be equal to 6 over 7. And if we have A and B, if A is this, if B is this, A intersect B prime is going to be any of the region that is in A and outside B. So it's going to be this region here. I don't think I'll be taking A-level with you guys. I know some teachers will take A-level together with the students. I'm not sure why. I've never had this motivation of doing that. Especially this year is the year where I seriously don't think they will welcome people who try to take A-level like casually, because they are trying to do all the social distancing thing. So this is definitely not a good year I personally find, okay, this is definitely not a good year for any teachers to try to attempt an A-level with a more, just as a test and a more casual kind of mindset. So, I don't think I will know the question in paper 1 unless someone were to send me paper 1. Like last year, someone actually did send me paper 1, so I did manage to take a look at paper 1. And even if I were to take the paper, right, if it is the same as last year, the script is going to be collected. So whatever information that I have, it will be based on just memory. It is not going to be very, very accurate also. So I'm really hoping that someone can pass me a paper 1. If I'm able to get hold of a paper 1, and if I can analyze the questions in paper 1, then on the 5th of November, I would like to share a bit of what I think can possibly come out in paper 2. And like what I was telling you, if you want to do a good analysis of what is going to come out in the pure math part of paper 2, you cannot just analyze paper 1 according to topics, because within topics there are also different ways of testing questions. So to be safe, right, I think we cannot sort it out by topics. We got to sort out the entire thing by question types. If the question type has not appeared in paper 1, for example, vectors, then there is still possibility that it will still appear in paper 2. That is in like, if it will still, that means vectors may still possible to appear in paper 2 as long as the question type has not appeared. So anyway, coming back to this part 1. Oh, but for the last few years, it was actually pretty easy to get hold of the paper 1. You know why? Because the students will be able to take paper 1 away from the exam hall. So everyone will have a paper 1. But this year, I'm really not sure. As in, like, last year I was already not sure, but somehow somebody actually got hold of the paper 1. But this year, I don't know. We want to find the probability of B when I'm given these 3 pieces of information. And I think finding the probability of B is actually pretty simple. If I were to just take this area, minus away this area, I'll be able to get the area of this B circle, correct? So to find the probability of B, I will just need to take the probability of A union B. Then minus away the probability of A intersect B prime. And this is going to be 6/7 minus away 1/3. This is equal to 11/21. This will be useful. Let me write it down here. Probability of B is 11/21. We want to next find the probability of A prime given B. The probability of A prime given B will be probability of A prime and B divided by the probability of B. Probability of A prime and B, the numerator here, if I were to just try to visualize it, AB, A prime and B is the region that is going to be outside A and inside B, so it's going to be this region. And in order for me to find this region, we will take this A union B minus away the probability of A, and that will give me this region. And we do have the probability of A here. So for the numerator, it will be probability of A union B minus away the probability of A. And this, I'll divide it by probability of B. So probability of A union B, this is 6/7 minus away the probability of A divided by the probability of B that we have found in the previous part. This gives us part 2 as 48/55. Okay, part 2. Then in part 3, we are supposed to be working on B and C. B and C, it is also given to me that they are independent of each other, which means that if B and C are independent, probability of B intersect C can be expressed as probability of B multiplied by the probability of C. Okay, since B and C are given to me as independent. So in order for me to find this part 3, probability of B prime intersect C. Maybe we should try to visualize this also. So let me try to sketch it on a Venn diagram for us to visualize. We have B and let's say C is this. So B prime intersect C is this. And in order for me to find this region, the area of this region, I'm going to take C, then minus away this overlapping region that is between B and C, and that we have the way to calculate it, B intersect C. So I am going to take the probability of C minus away the probability of B intersect C. Probability of C, this is given to us as 2/3. Minus probability of B intersect C will be the probability of B, which is 11/21, multiplied by the probability of C, which is 2/5. Oh, 2/5, I've written it wrongly. So this is 2/5. and this is going to be equal to 4 over 21. Well, I think part 1, part 2, part 3, they are pretty simple. Part 4 is the one that require us to react to the context. It's harder for us to generalize something that is in part 4. So although I'm going to be doing this part 4, but I wouldn't say that the solution is going to be exactly the same if it were to appear in another similar question, but the idea is going to be somewhat similar. And the way to approach this, the idea to approach this is to actually do your trial and error and exploration. Let me show you what I mean. Is there anything that I should try to record down first? I think this is fine, so I'm going to erase this. Okay, we are going to be looking at A intersect B prime intersect C. Actually, I've already drawn a better diagram here. Let me make use of this diagram. Oops. Okay, I need you guys to visualize this together with me, okay? So the region where we are, the region that represents this A intersect B prime intersect C. The region that this is representing is the region that is inside A, outside B, and inside C. So it is going to be this region here. Okay, so this region is A intersect B prime intersect C. We are going to try to calculate the greatest possible and the smallest possible of this A intersect B prime intersect C. And let's start with maybe the greatest possible. Yeah, I think I know why you asked this question, because this question is actually not easy to do, because you need a lot of like on the spot analysis, right? That's why that's why we will have this tendency to want to know whether there's a general approach. But sadly, I feel that the general approach is to do your trial and error on the spot by adjusting, by making use of the Venn diagram and doing some adjustment to the area through your visualization. For example, right, it is actually quite easy for me to show you using this whiteboard here. So I need you to try to focus on this area. This area is A intersect B prime intersect C. Okay, let's see how we can do the adjustment so that this region here, right, is going to be as big as possible. I'm going to erase this, okay? So I need you to visually take note that this is the region that we are looking at. How will this region become bigger? It will become bigger if, let's say, I start to shift this into A. Can you see? It was originally like this, and the moment when I shift this in this way, it will become bigger and bigger and bigger. So hopefully I can shift it entirely into A, into something that is like this. Then this will be the biggest possible. Let me show you one more time, okay? It was like this. So the more I can shift this into A, the bigger this region is going to be, right? So it will become bigger and bigger and bigger. And hopefully it is possible for me to shift the entire thing into A in this way. Is it possible? Let's test. So for this region here, this region which is probability of A intersect B prime. Okay, for this region here, probability of A intersect B prime, we have found out about it just now. Just now, A intersect B prime, it is actually given to us. So A intersect B prime, this is equal to 1 over 3. And we are looking at this region, right? So for this region over here, this region is going to be inside C and outside B. So this region over here is the probability of B prime intersect C. Okay, this entire region here, B prime intersect C, outside B and inside C. And this we have already calculated here. And just now we have found out that this was 4 over 21. 1/3 is equal to 7/21, which means that this area is going to be bigger than this area, which means that this is possible, which means that when I attempt to push this more and more into A, it is possible that this entire region here, which is B prime intersect C, can go entirely into A like this. Okay, and this is the maximum it can get. So therefore, the greatest possible of this probability of A intersect B prime intersect C, with the greatest possible of this is going to take up exactly the same as this probability of B prime intersect C. So the greatest possible is 4/21. And what it takes is challenging because we got to do this visualization on the spot. And of course, the question is, how do we know that we are supposed to do this kind of shifting, and furthermore, in the exam, it's not like you can shift the circle here and there as easily as this. And I guess that is why this kind of question is challenging, especially if it appears in an exam. You will have a few chances of trying this out first, because A-Level has said this a few times. And if you have been doing prelim papers, you will also realize how many schools have been setting this also. So I can make use of all these chances to practice. And in order for us to make this region here, we are still focusing on this region. This region is A intersect B prime intersect C. In order for this region to be as small as possible, the least possible, just now to make it as big as possible, we are trying to push this C into A as much as possible so that this region becomes as big as possible. So to make this as small as possible, I'm going to move C out as much as possible, which means that this region here must be as big as possible. And I'm going to try to just make this region so big that it occupies everything that is outside A and B, this region. Okay, because the maximum I can push this out is if this region can really take up the entirety of the outside. The entirety of the outside as in like, I'm going to be looking at 1 minus probability of A union B, where I'm looking at the entire region that is outside. And this is going to be 1 minus away. A union B is given to me as 6/7. So this is 1/7. And I'm going to let this region here, because the maximum this region can get, will be filling the entire space that is outside. So I'm going to let this region here, which is the region that is outside A and outside B and in C. I'm going to let this region be 1/7. The bigger this region is, the smaller this will get. So now the biggest possible I'm letting it be is 1/7, which will then help us to find the smallest possible of this probability of A intersect B prime intersect C. This will be calculated by taking this area here. This area here is the probability of B prime intersect C. Then minus away this 1/7. So B prime intersect C, we have calculated it just now, that is 4/21. Minus 1/7, this is going to give us 1/21. Okay? And my suggestion is also, I'm not sure whether this is clear enough for you, okay, but I believe that it is going to give you a rough idea of how to do this kind of question. So my suggestion to you is, if you're not very comfortable with this, consider redoing this question number 8 again. As in like question number 8 part 4 again. And you can try to aim to come up with the solution together with your analysis independently. And only when you can do that independently, then maybe you had a good enough practice on this question. what I'm trying to say is it's not just dependent on how you understand some other people have done this, but it is also to make use of your own analysis and judgment to see whether you can analyze based on the areas to determine the greatest possible and the smallest possible. Okay, but this is a challenging question, I find. Next, let's take a look at question number 9. 9 is pretty okay, I feel. 9, we have the word jewelry. So we have J, E, W, E, L, L, E, R, Y. 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. Without any restriction for these 9 letters, it is going to be arranging all the 9 letters, then 3 E's divided by 3 factorial, 2 L's divided by 2 factorial. This will give me part 1's answer as 30240. Then part 2. Part 2, we are supposed to arrange this with starting at L, and there must be at least 2 other letters in between any 2 E's. Okay, at least 2 letters in between any 2 E's. So the first case that I can think of will be, it has to start with L. So this one, we cannot do anything about it. And I'm going to make sure that there are at least 2 letters between the 2 E's. If one L is removed, then I will have a 1, 2, 3. I will have a 1, 2, 3, 4, 5 letters to be arranged such that there will be at least 2 between the 3 E's. So one of the possible ways of arranging will be this, then E, then 1 letter, 2 letters, E, then 1 letter, 2 letters, E. So one of the possible ways of arranging will be something that is like this. And of course, if it is this kind of arrangement, we can also see it as E, letter, E, letter, E. So it can also be this, then another letter. L is fixed, so it is not going to be part of my arrangement. So for this particular arrangement, it is going to be 5 factorial. I'm not arranging the E's because they are fixed at this position. So it will just be this. So 5 factorial. It is the same for this 1, 2, 3, 4, 5 distinct letters. So another 5 factorial. So it will be 5 factorial plus 5 factorial, or 5 factorial multiplied by 2. This is going to give me a 240. This is if there were to be 2 letters between the 2 E's. I have another case which is 3 letters between the 2 E's. There are 5 other letters for me to be arranging. So 3, then E, then it must be 2, then E. Where this must be together in this way. Or another possible way, it will be E, then 2 letters, E, then 1, 2, 3, 3 letters. We have this. So this will be another way. For this, it will also be 5 factorial. For this, it will also be 5 factorial. So 5 factorial plus 5 factorial will be 5 factorial multiplied by 2. This will also be 240. So the total number of ways that we are talking about, it is going to be 240 times 2. My answer for part 2 is 480. And part 3 is a very standard question. Since now you guys have already finished your prelim, I'm assuming that you know exactly what to do when it comes to a question that is like 9A part 3. Okay, but just in case you are still unfamiliar with this, my suggestion is to really sit down and patiently think of a general strategy to deal with something that is like part 3. Okay, because it is a very standard question that always comes with pretty high marks. So if this year this were to come up for the A-levels, it will be a disadvantage if most people can actually do this question except you. That is why you need to set for yourself a high criteria for this. Okay, you must know how to do this question. To do this kind of question, the idea is to try to manage identical objects. One mistake that students tend to make when it comes to this since there are 9 letters, 1, 2, 3, 4, 5, 6, 7, 8. Since there are 9 letters here, so one mistake that some students tend to make is to do a 9 choose 4, then multiply by 4 factorial and divide it by 3 factorial, 2 factorial. I believe some of you probably have had made this mistake in the very beginning of your PNC, but now you shouldn't be making this mistake already, because this calculation is just illogical. You know why illogical? Because out of 9 objects, we are just choosing 4, out of 9 letters, we are just choosing 4 letters. And then, how can within these 4 letters hold 3 identical letters and another 2 identical letters? It is physically just not possible. That is why this is a bad strategy. But this also tells us what we are supposed to be focusing on. The reason why we couldn't do this was because in this 4 factorial, we do not know how many identical objects are going to be appearing. That is why to do this kind of question, part 3, we will always do it by cases. And the way that you are listing down the cases has a particular structure. The structure is based on the number of identical objects that you expect will appear in the 4 letters. This kind of question is usually like that. You have to list down the cases. This I don't think you can skip, and I don't think we have a good rule for it because it really depends on the question. But the way that you list down the cases depends on how you are going to perceive identical objects to be appearing. For example, I will always start with all distinct letters. So I will make sure that there will be, the first case that I'll be analyzing will always be when there will be no identical letters, which means that the letters that I will be analyzing will be J, E, W, L, R, and Y only. It will only be these few letters that will appear. 1, 2, 3, 4, 5, 6. So out of 6 letters, I will choose 4 and multiply it by 4 factorial. I'm safe because all these are distinct, so I do not need to take care of any identical objects. This is going to be equal to 360. Case 2. Like what I was telling you, I'll list down my cases based on the number of identical objects that I perceive. So of these few letters, if identical objects were to be appearing, one of the possible cases will be when 2 E's are appearing, which means that here will be 2 distinct objects, 2 distinct letters, and the 2 letters will be either J, W, L, R, or Y. So I have 1, 2, 3, 4, 5. Out of 5, I will choose 2 letters to be combined with the 2 E's. Arranging them, it is going to be 4 factorial. But because now I know that there's going to be exactly just 2 identical objects, I know I can safely divide it by 2 factorial because it is going to be within these 4 letters that I'm calculating, that I'm looking at. So for this, it is going to be 1, 2, 0. Then we have case 3. Again, let's base it on the identical objects that I am imagining. So 3 E's and then 1 more letter, and this letter will compose of again J, W, L, R, or Y. So this will be out of 5, we will choose 1. 4 factorial, I know there will be exactly 3 identical objects, so this is going to give me a 20. What other cases can we think of such that there will be identical objects? How about E, E, L, L? Let's start to involve this L. So E, E, L, L, it is going to be just simply 4 factorial divided by 2 factorial, 2 factorial. This is going to be equal to 6. We have still one more case. The one more case will be LL, then letter, which means that in here we will be looking at J, E, W, R, and Y. Okay, we'll be looking at this 1, 2, 3, 4, 5 again. Out of 5, we will choose 2. Combining with these 2 letters, 4 factorial divided by 2 factorial. This is equal to 1, 2, 0. So now I have sieved through all the possible cases of identical objects appearing in the 4 letters. So the total is going to be equal to 360 plus 120 plus 20 plus 6 plus 120. This is equal to 626, the total number of ways. And B is confusing, not because of the calculation, but because of the way the phrases are being presented. I found it a little bit confusing, but because I have done something similar before, that's why I know what to watch out for, which is for the children to be not all seated together. We want to make sure that the children are not all seated together. It's easy to misinterpret this as the children must be all separated. But for the children to be not all seated together, it does not imply that the children must be all separated, because it is still possible for two of them to be seated together, then one is like sitting somewhere away. It will still satisfy the conditions such that the children are not all seated together. So in order for me to calculate this, I'm going to first try to calculate the probability where the parents are seated together and the children, there are 3 children, together with 5 other people, 1, 2, 3, 4, 5. I'll just arrange them with the 2 parents being seated together. Then I'll minus away what the question says that it doesn't want, which is for the children not to be, which is to minus away when the children are all seated together. So I'm going to minus away this C, this, and 1, 2, 3, 4, 5. So for this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 objects. 9 minus 1 factorial. Then the parents, 2 factorial. And I'll minus away this case, 1, 2, 3, 4, 5, 6, 7. We have 7 objects, 7 minus 1 factorial. For the 2 parents, 2 factorial. For the 3 children, it will be 3 factorial. This will give me my answer for part B, and it will be 72000. Okay, not a difficult question, but it is just that this phrase here, where the children are not all seated together, can be confusing. And the thing is, it's not the English that is confusing. We will find this confusing because of our experience in P&C, I think. Because of our experience in P&C, we are too used to having objects being all separated. And that's why when we have a phrase that is like this, when the children are not all seated together, it reminds us, the key learning point of one of the key learning points of statistics, which is to be able to interpret a real life scenario as how we usually communicate in terms of our, which is to be able to translate how we usually communicate logic in our real life. Like for example, children are not all seated together. It is a very logical thing to say, like in a day-to-day circumstances. Okay, it's not like you're going to say this all the time, but it's not unusual way to express in terms of English. But what we are trying to do is to make sure that we read English as English and we learn how to translate that to math. So I guess this is a good reminder. If we were to use too much math experience to read English, we may get this wrongly. By making sure that all the children are separated. Let's look at the last question, which is question number 10. 11 is a correlation linear regression question, so I'm going to be skipping that question. So question number 10, a hypothesis testing question. We are now looking at the amount of sodium that is in a packet, and the mean is assumed to be the mean is known to be 1053. Some alteration is done to the production process, and 50 packets of potato chips are going to be analyzed for the amount of sodium that is inside. the raw data is given to us as this. We are supposed to do a 5% level of significance for the mean amount of sodium that is in a packet of potato chips, and we are trying to analyze whether it has changed. I'm going to first define the notation that I'm going to be using for the population mean, the mean of X. So I'm going to let's say mu be the mean amount of sodium, because it is the population mean, so it should be the mean amount of sodium in a randomly chosen packet of potato chips. In a randomly chosen packet of potato chips. And we are supposed to be testing whether mu is going to continue to be 1053 versus whether it is not 1053. The sample that we are looking at has a size of 50. The mean of this 50 is going to be calculated by summing this 1050 divided by n plus 1050. So this mean is going to be equal to 58.0 divided by 50 plus 1050. This is going to be equal to 1051.16. This is the evidence that we have collected based on the 50 sample, and this evidence supports our alternative hypothesis, which means that we are seeing that the sample mean has changed. So we are looking at this sample mean. It gives me an evidence that suggests that the population mean has changed. We're going to try to analyze whether it has whether this is going to be an evidence that is strong enough to suggest that there's a change. Let's try to work out the test statistics. For the test statistics, we need the population variance. And if you were to look at the question, we do not get population variance from the question. So we are going to make use of the sample statistics to calculate the unbiased estimate to the population variance. And that will be 1 over n minus 1 summation of x minus 1050 squared minus summation of x minus 1050 squared divided by n. This will be 1 over 50 minus 1. Then this is 2326 minus away this is 58.0 square divided by n. N is equal to 50. And the population variance is going to be equal to 46.096. This will help us to come up with our test statistics, which x bar, which is x1 plus x2 plus x3 all the way until x50 divided by 50. This x bar will follow a normal distribution with a mean, population mean, 1053, and a variance of 46.096 divided by n, which is 50. And if you were to look at the question, it has never been mentioned whether x follows a normal distribution. But since n is large, that is why we could write down this and as an approximation because of the central limit theorem. Since n that we are working on is considered as large. If I were to press it into my GC, I will be able to get the p-value. And the p-value from my GC is 0.055322. And what we can see now is a p-value that is bigger than the level of significance, 5% level of significance. So we can add a conclusion that is like this. Since this p-value here is bigger than 0.05, it means there is going to be insufficient evidence. insufficient evidence that the mean amount of sodium in a packet has changed at 5% level of significance. It is the mean amount that we are analyzing. That is why in your conclusion, please make sure that you are suggesting that there is insufficient evidence that the mean amount of sodium has changed. If you were to write that there's insufficient evidence to suggest that the amount of sodium has changed, I'm not sure. Maybe you may get 1 mark minus off, or you will not get the marks for the conclusion, because we are analyzing the mean amount, not the specific amount. P-value. The meaning of p-value was like, I think we did it once, right? So we were saying that for the meaning of p-value, we will always be, one way to perceive p-value is to try to compare it to the level of significance. And for H0 to be rejected, let's do a quick recap on p-value, okay? So what is the, because hello, you're asking, right? What is the meaning or the definition of p-value? Because most of the time they will ask you this, part 2. Explain what is 5% level of significance. Then once in a while, they may ask you this p-value, which somehow has gotten quite a fair bit of momentum. I'm not sure why. Well, last time, not many schools like to ask about this p-value, but somehow in the last few years, it seems like more and more schools has been starting to ask about this p-value, p-value, p-value. So, okay, let me write down this part 2 first. Then let's recap, what is the meaning of p-value. Which was the paper that we have done together that has this p-value? Then we were trying to, I think River Valley, right? Was it River Valley? We did a paper, then I know there was this p-value, then we were trying to discuss about this p-value, then someone was saying, okay, p-value is the minimum level of significance such that H0 is going to be rejected. So, okay, let me just write down my reply to part 2. Explain what is 5% level of significance. So I'll say something that is like this. It means that there is a probability of 5% level of significance, so a probability of 0.05 that the mean amount of sodium is when in fact it has not. Where the mean amount of sodium is wrongly concluded to have changed when in fact it has not. Why will this be happening? Because of this. The reason why this can potentially happen is because we are looking at a sample of 50. And the worst was, we actually found an evidence that suggests, the evidence that we have found was based on this. We have found an evidence that suggests that it is this is 1051.16. We have found an evidence that is actually going to be not 1053, which means that the evidence suggests that there is a change. But because this is not exactly the entire, these 50 samples is that not exactly a true representation of the entire population. That is why, although we have found an evidence that suggested a change, there's always a chance that this change is wrong. It is wrongly concluded, because this is a sample and we are trying to use the sample data to try to analyze the population data. And for the population, I don't know, maybe there will be, if this is a sugar factory, maybe there's going to be 1 million packets of sugar that is in the store. So it is an unfair test, right? By taking 50 to reject 1 million. That is why, although an evidence has been found that suggested a change, it is always possible for this conclusion, based on the evidence to be wrong. And as for the p-value, we have discussed it the last time. P-value is, let's say p-value is taken from the perspective that, for example, H0 is rejected. So if H0 is rejected, we know that the p-value has to be less than the level of significance. So it is this. Okay, let's say we are talking about level of significance as alpha. So we are talking about 100 alpha% level of significance. So p-value must be less than alpha. H0 rejected, p-value is less than alpha. So based on this, in order for us to define p-value, we have talked about it like this way. H0 rejected, p-value less than alpha. So to define p-value, we will go this way instead, which means that we will see alpha to be bigger than this p-value here, whatever the value is. Let's say 0.00, let's say 0.533, for example. So if we were to go this way, as long as alpha is bigger than p-value, this will tell me that H0 is going to be rejected. So what is p-value? P-value defines for me the minimum alpha such that H0 is going to be rejected. P-value represents the minimum level of significance such that the null hypothesis is going to be rejected. Okay, this is to answer your question on the definition of p-value. We will make use of this. Next, part 3. Part 3 of this question. A second test is conducted with the same. The second test is conducted. Now we are looking at alpha percent level of significance, where alpha is going to be some integer value. However, he is going to be having a different conclusion. Based on part 1, the conclusion is that there is insufficient evidence. So based on part 1, we know that the p-value, insufficient conclusion. So the p-value is going to be bigger than the level of significance, bigger than alpha over 100. Okay, this was from part 1. So in this case, what is the range of alpha such that we will derive at a different conclusion? So for a different conclusion, we are going to be letting the p-value. In part 1, p-value was bigger than. So for a different conclusion, we will let p-value be less than the level of significance, which means that there is sufficient evidence to suggest a change from 1053. So in this case, alpha is going to be bigger than 100 multiplied by the p-value from part 1. P-value from part 1 is 0.055322. This tells us that alpha is going to be bigger than 5.5322, and since alpha is an integer value, the range of alpha will be bigger or equal to 6. This is part 3. And in part 4, without performing another test, can we try to explain whether the conclusion in part 1 will be, whether the conclusion will be different from part 1 if the alternative hypothesis is changed to decrease instead of not equal to. So now we are talking about H0, which is still going to be equal to 1053. And this time we are talking about a decrease. So this is supposed to be less than 1053. Well, let's see whether the conclusion is still going to be the same or is it going to be different. So from a two-tailed test, we have switched to a one-tailed test. For a two-tailed test that we carried out in part 1, we saw the p-value, which was this. So the p-value in part 1, it was 0.055322, and this was for a two-tailed test. And now we are looking at a one-tailed test, which means that the p-value for a one-tailed test will be 0.055322 divided by 2. This will be the p-value for a one-tailed test, and this is equal to 0.027661. And this is less than 0.05 because we are talking about everything remain the same, which is still this 5% level of significance. And since now the p-value is less than 0.05, previously it was bigger, the p-value was bigger than the level of significance, so there were insufficient evidence to reject. Now the p-value is less than the level of significance, that means there is going to be sufficient evidence to reject. So will the conclusion be different? The conclusion will be different. Okay, because we are concluding now that there is sufficient evidence that the mean amount of sodium has decreased. And the last part, part 5. Part 5, we are actually doing something that is entirely different. Okay, not exactly entirely different. We are still looking at the same scenario. We are going to be carrying out another test. We are still going to be looking at H0, where mu is equal to 1053. And we are going to be testing whether the mean amount has decreased. So we are going to be testing H1 such that mu is going to be less than 1053. Okay, there's going to be a decrease. So for this, we are now looking at another sample, and this time this sample has a size of 40, and we are supposed to find the range of this y bar. The population variance is now given to us. The population standard deviation is 6, so the variance is going to be 6.0 square. And the test statistics, will be y bar that will follow a normal distribution of 1053 and a variance of 6.0 square divided by the sample size. And we are still not told whether y follows a normal distribution, so this is an approximated distribution by the central limit theorem. Since n that is given to me as 40 is still somewhat large. And according to the question, a rejection is taking place. The conclusion is such that there is going to be a decrease. There is sufficient evidence to conclude that there's a decrease, which means that if I were to try to analyze y bar on a bell curve, this bell curve will be from my test statistics. So it is going to be based on y bar, where the center here is 1053. It is going to be a left tail test, and we are talking about 5% level of significance. So the critical region is going to be 0.05. And since there is sufficient evidence for a decrease, that means the evidence here, y bar should be within the critical region here. And if you were to analyze the area that is on the left hand side of y bar, we can see that for rejection to take place, the area that is on the left hand side of y bar, this area has to be less than 0.05. And using this normal distribution, I'm going to just press this into the calculator. We're going to get y bar directly. Y bar here is going to be less than 1051.4. And to one decimal place, this is going to be my answer. This is the range of values for y bar such that there is enough evidence to conclude that the mean amount of sodium has decreased. Do we need to give any other assumptions in order for us to carry out this test? Nope, we do not need to. Why? Because n is large. And since n is large, we can make use of the central limit theorem to approximate y bar as one that follows a normal distribution. Actually, I've already written it down here. So is it necessary for us to give any more assumption? No, it is not necessary because n is large. So through the central limit theorem, y bar will already follow a normal distribution. Okay? And like what I was saying, I'm going to skip the last question since this is not going to be tested this year. Correlation linear regression. And okay, we have already finished our section B. And I will want to do section A. It looks interesting. Central limit theorem central limit theorem is a kind of assumption. I'm not sure how to place it. I think central limit theorem is a theorem. Central limit theorem is a theorem that governs the rule such that if you were to combine a lot of random variables together in the combined form, it will follow a normal distribution. So let's just treat central limit theorem as a theorem. The assumption is, for example, we need to assume that y follows a normal distribution. Then yes, we need to y because n is small, and because n is small, we cannot make use of the central limit theorem to approximate y bar as a normal distribution. That is why we need to assume that y follows a normal distribution. If it is that case, I would say that we are talking about the assumption. Okay. I will want to do section A of this. So let me see. Yep. So this Friday I will